Brothers' flight in 1903, and all the way to the present day, mankind has been fascinated by taking to the skies. Once thought to be impossible, heavier-than-air flight is only a reality because of the lift generated by aircraft wings. But lift is a complicated topic, and even to this day, engineers have lengthy debates about how it's created. So what exactly is lift? When fluid flows past an object, or an object like this plane wing moves through a stationary fluid, the fluid exerts a force on the object, which can be split into a component acting in the same direction as the fluid flow, called drag, and a component acting perpendicular to the flow direction, called lift. When talking about lift, we're mostly interested in streamlined bodies like this airfoil, which are carefully designed to produce a lot of lift, but to minimize drag. Lift-producing airfoils can obviously be found in airplane wings, but also in many other applications, like wind turbine blades or propeller blades. They're also used in the wings of Formula One cars, which are designed to generate downforce so that corners can be taken at higher speeds. Airfoils come in a huge range of shapes and sizes. One designed for an aircraft wing won't be optimized for a propeller blade, for example, and a wing designed to fly at supersonic speeds will have a very different profile compared to one designed to fly slower than the speed of sound. Airfoil profiles can be defined using a few different parameters. The forwardmost edge of the airfoil is called the leading edge, and the trailing edge is at the back of the airfoil. Drawing a straight line between the leading and trailing edges gives us the chord line. The angle between the chord line and the flow direction is called the angle of attack. Drawing a line which is midway between the upper and lower surfaces gives us the mean camber line. Camber describes how curved an airfoil is. We can have positive camber or negative camber, and a symmetrical airfoil has zero camber. Camber and the angle of attack are important parameters that will have a large influence on how much lift an airfoil can generate. So how does a humble teardrop shape generate enough force to lift heavy aircraft off the ground? As the fluid flows around the airfoil, it creates two different types of stress which act on its surface. First, we have the wall shear stresses. These stresses act tangential to the object's surface and are caused by the frictional forces that act on the airfoil because of the fluid's viscosity. Then we have the pressure stresses. They act perpendicular to the object's surface and are caused by how pressure is distributed around it. Lift is the resultant of these two stresses in the direction perpendicular to the flow. The only way a fluid can impart a force onto an object is through these stresses. Integrating the stresses in the lift direction over the surface of the airfoil gives us the lift force. For streamlined bodies like airfoils, the shear stresses will mostly be acting in the same direction as the flow. They will make a large contribution to the drag force, but won't contribute a significant amount to the lift force. And so we can neglect them and say that the lift acting on an airfoil is caused by the way pressure is distributed around it. A typical pressure distribution looks something like this. The pressure is low above the airfoil and high below it, which creates a net force with a large component in the lift direction. If we plot the pressure profile along the top and bottom surfaces, we can see that the low pressure on the top surface is larger in magnitude than the high pressure on the bottom surface. So the suction pressure on the top surface is what contributes most to the total lift force. We can also see that the majority of the pressure difference is coming from the forwardmost part of the airfoil. In truth, there's nothing particularly special about the shape of an airfoil that allows it to generate lift. Any object that creates an uneven pressure distribution will generate a force in the lift direction, like a flat plate at an angle relative to the flow, for example. Airfoils are just optimized shapes that have been carefully designed to have high lift-to-drag ratios. Without a difference in pressure above and below an object, there can be no lift. A symmetrical body, like this bullet, doesn't generate any lift force because there's no pressure difference around it. So we know that lift is caused by the pressure distribution around the airfoil. But where does the pressure distribution come from? The answer to this question is complex, and there's much debate about the best way to explain it in a concise way. We can broadly split the different explanations into two groups, those based on Bernoulli's principle and those based on Newton's third law. Bernoulli's principle explanations focus on the velocity of the fluid. If we look at how fluid flows around the airfoil, we can see that close to the leading edge, there's a point where the fluid velocity is reduced to zero. This is called the stagnation point. Outside of the thin boundary layer surrounding the airfoil, the fluid flowing above the stagnation point over the top surface of the airfoil travels faster than the fluid traveling over the bottom surface, as we can see from these particles. Bernoulli's principle tells us that when the velocity of a fluid increases, its pressure must be reduced, which is just a statement of the conservation of energy. This means that the increase in velocity above the airfoil creates an area of lower pressure, and the reduction in velocity below it creates an area of higher pressure, and this pressure difference creates the lift force. But then, we need to explain what causes the difference in velocity. One explanation is that the geometry of an airfoil causes the flow to be pinched together above the airfoil, but not below it. Because of the conservation of mass, this results in increased velocity above the airfoil. A more complete but less intuitive explanation for the difference in velocity is based on the concept of circulation. The flow around an airfoil can be thought of as the superposition of idealized uniform irrotational flow and circulatory flow. Without circulation, the flow around the airfoil would look like this. This is clearly non-physical, since the fluid can't turn such a sharp corner at the trailing edge, and so the airfoil must be generating some circulation. If we impose a condition that says the flow above and below the airfoil must be parallel when leaving the trailing edge, we can calculate the exact amount of circulation that must be generated by the airfoil to do this. This is called the Kutta condition. Circulation has the effect of accelerating the flow above the airfoil and delaying the flow below it, which gives us the explanation we need so that we can apply Bernoulli's principle. What about the explanations of lift that are based on Newton's third law? These don't consider the velocity above and below the airfoil, but instead look more generally at the behavior of the fluid. If we look at a wider area, we can observe that the effect of an airfoil can be felt far beyond its immediate vicinity. Upstream of the airfoil, the flow is being swept upwards, which is called upwash, and downstream the flow is deflected downwards, which is called downwash. A very large volume of air is being displaced by the airfoil. Newton's third law tells us that for every action there is an equal and opposite reaction. The airfoil must be imparting a force on the air to create the downwash, and so based on Newton's third law, there must be a corresponding reaction force acting on the airfoil. In other words, an airfoil generates lift by turning the incoming air downwards. We can use the concept of circulation again, this time to explain how the upwash and downwash are created. In summary, a lift force acts on an airfoil because of the pressure distribution around it. The exact cause of this pressure distribution is complex and can be explained in several different ways, which approach the problem from different angles. Explanations based on Bernoulli's principle and on Newton's third law provide valuable insight into how lift is generated, although both approaches have limitations, partly because they're based on cause and effect relationships. The problem is that there isn't always a clear cause and effect relationship between the different phenomena which are involved in generating lift. Whether we're talking about the fluid velocity, the pressure distribution around the airfoil, or the downturning of the fluid. In reality, all of these things are happening simultaneously and are mutually interacting. Nevertheless, these explanations are useful and can lead to a more intuitive understanding of lift. We can easily imagine, for example, that increasing the camber of an airfoil will allow it to deflect a larger amount of fluid, and so will increase the lift force. The same is true for the angle of attack. Increasing the angle of attack deflects more fluid and increases lift. However, there are limits to this logic. Once the angle of attack reaches a certain critical value, we can observe a sudden decrease in the lift force. For this airfoil, it occurs at around 16 degrees. At this angle of attack, the boundary layer is no longer able to remain attached to the airfoil, and it detaches from the surface, creating a wake behind it which affects the pressure distribution around the airfoil, significantly reducing lift and increasing drag. I covered flow separation in detail in my video on aerodynamic drag. The sudden reduction in lift is called stalling, and it can be very dangerous for aircraft. Different airfoil shapes can have drastically different lift characteristics. This airfoil is cambered. If an airfoil is symmetrical, and so has zero camber, the lift force will be zero for zero angle of attack. Aerobatic aircraft usually use symmetrical airfoils since they allow planes to fly upside down more easily. Lift is generated by lifting the nose of the plane to create an angle of attack. Modern aircraft wings are equipped with flaps and slats, which allow the shape of the airfoil to be adjusted and optimized for different phases of flight. During takeoff, for example, you want high lift. Extending the flaps increases the camber of the wing, which increases lift, and so flaps are extended during takeoff. But the extra lift comes at the expense of increased drag, and so the flaps are retracted when cruising, since high lift is no longer needed and drag should be minimized to improve fuel consumption. This video has really only scratched the surface when it comes to developing a complete understanding of lift.